Greetings once again and welcome to the third lecture on special or select topics in classical mechanics, and this is the second lecture on the equations of motion, which is our first unit. And we begin with where we left last time, which is the consideration of Newton's third law, and this is stated as action and reaction are equal and opposite, and this can be stated exactly on the same footing as Newton's first law and the second law. Now, there are a few important points which I will recapitulate quickly. First, that the first law of Newton, which is the law of inertia or Galileo's law of inertia, is a separate law by itself. It cannot be considered as a special case of the second law by putting f equal to 0 in f equal to ma. So, whenever you make use of the second law, the first law is already implicit in it, implicit in the sense implicitly referenced in it, because unless you identify an inertial frame of reference, you do not touch the second law. So, you first identify a frame of reference in which motion is self sustaining, and this is what defines equilibrium. Once you recognize this, you can ask what is it that is responsible to change the equilibrium, and that is answered by second law, that there is some interaction, some physical interaction, which is what we call as the Newtonian force. So, this comes into consideration only after recognition of the first law of inertia. This is sometimes stated by saying that when you want to identify what a frame of whether or not a frame of reference is inertial, you say that an inertial frame of reference is one in which Newton's laws hold, but that is like a cyclic statement. It is correct, it is formally correct, but it really does not take you anywhere, because you define Newton's laws with reference to inertial frames, and then if you define inertial frames with reference to Newton's laws, then you are really not out of the cyclic argument. So, you need some kind of mechanism to come out of the cyclic argument, and this is what develops a notion of a physical interaction in your mind, because in the absence of any physical interaction, if you decide that motion is self sustaining in a certain frame of reference, then it is this frame of reference that you would regard as an inertial frame of reference, and in this frame, if you now perceive any change in equilibrium which manifests as acceleration, then you call the agency which caused this change as the Newtonian force. So, F equal to ma comes into picture only after you have identified an inertial frame of reference invoking the first law. These two laws, the first law which we got from Galileo's experiments and from his observations, and the second law which comes from Newton's reasoning in the explanation with regard to the departure from equilibrium, these two laws were not derived from anything. These are fundamental principles on which the rest of mechanics stands. So, this provides you with a platform, and everything else in mechanics can in fact be derived out of this. And on the same footing, one could state the third law, which is there on the screen in front of you, that action and reaction are equal and opposite. This can also be stated exactly on the same footing as a fundamental principle not derived from anything else, okay, but which is an equal partner along with the first and the second law in providing you with a foundation on which the rest of mechanics stands. So, one can certainly learn the third law exactly on the same footing. An immediate consequence of the third law is what you see on the screen, and we discussed this briefly last time, that if you write action and reaction are equal and opposite, as in this expression over here stated mathematically as F12 equal to minus F21, then it immediately follows that the total momentum is conserved, its time derivative vanishes and therefore it is a constant of motion. In other words, we get a conservation principle from a law of nature. It is the third law that I am referring over here. The third law now takes the place of a law of nature, and this gives us a basis to determine a conservation principle, namely the conservation of linear momentum. Now let us ask this question: are the conservation principles consequences of the laws of nature? The answer would be yes, if we accept the logic as we just discussed. That is exactly what we did. We began with the law of nature, namely the third law of mechanics, and from that we deduced the conservation of linear momentum. We can also ask, are the laws of nature the consequences of symmetry principles that govern them? Now this is a new question which some of you may not have considered earlier. Are the laws of nature consequences of the symmetry principles that govern them? This is a very fascinating question that can in fact be asked, and the mindset of physicists really underwent a sea change since Einstein's special theory of relativity, and this was 1905, and Einstein, this came out of his discussion of understanding of the electromagnetic phenomena and electrodynamics and so on. I will be discussing some of this in a later unit when we come to special theory of relativity and toward the end when we also introduce ourselves to electrodynamics. But essentially until Einstein's special theory of relativity, the conservation principles were considered to be results of the laws of nature, as we just saw. But since Einstein's work, physicists began to analyze conservation principles as consequences of certain underlying symmetry. Now this is a completely new approach, new not anymore since it has been with us since Einstein's thought process, so not new in that sense of the term, but new in terms of the context in which Newtonian mechanics is normally discussed. And what this consideration allows you to do is you are able to actually deduce laws of nature by examining these connections between symmetry and conservation laws. So these connections reveal to you what the laws of nature are, which is what a physicist is interested in, and this therefore gives you a mechanism, a tool, a pathway, some sort of a roadmap to discover new laws of physics, and that is always a fascinating issue because we do not even know if we know today already all the laws of physics. We do know a lot, but whether we know everything, are there some other laws which we are yet to discover, and the physicist's quest will be directed toward discovering these additional laws if there are any, and we do not know whether there are or there are not. So before we proceed, we let me excuse me, give me a moment. So before we proceed, I would like to show you another connection between symmetry and conservation laws, so that you know this starts becoming a part of our thought process. Consider the angular momentum, and you know it is defined as r cross p in classical mechanics. Obviously there is a certain point of reference with respect to which you measure the angular momentum, either a point or an axis or whatever, and we are going to consider angular momentum of a system which is subjected to a central force. Now what is a central force? A central force is one which is directed along the radial line. Okay, that is called a central fold because it has got that central field symmetry. Now, if you look at the torque, which is the rate of change of angular momentum, so I write d by dt, the time derivative of the angular momentum, which is r cross p, and this will be dr by dt cross p plus r cross dp by dt, right. There will be two terms in this, and out of the two terms dr by dt cross p will vanish, because dr by dt is the velocity which is collinear with the momentum. So, the cross product of these collinear vectors vanishes, and the second term, which gives you r cross dp by dt, gives you r cross f, which is the torque. Now, our interest is in a particular force which has got a special symmetry. This is the radial force, it is directed along the radial line. So, this force has got a certain magnitude and a direction which is along the position vector r. So, this force becomes collinear with the position vector r, and again the cross product of these two vectors vanishes. So, you immediately see that the torque would vanish for this central force, and if the torque vanishes, then dl by dt becomes 0 and L becomes constant. So, the angular momentum is a constant of motion for this particular case. What have we seen? That if there is a symmetry, if there is a radial symmetry, if the force is the central field force, then the angular momentum is conserved. So, we are meeting once again a connection between symmetry and conservation law. So, the fact that F is along ER is a symmetry, is a statement of symmetry, that L is constant is a conservation principle. Now, we are going to discover that this relationship between symmetry and conservation law is in fact so intimate that it allows us to actually derive Newton's third law using symmetry argument. Now, this is a very novel approach from the point of view of traditional orthodox Newtonian mechanics, not new in the historical sense. People have known this for more than 100 years, okay. So, it is not new in that sense, but new from the point of view of traditional orthodox Newtonian mechanics, in which Newton's third law was always regarded as a fundamental law of nature on the same footing as the first and the second law, that it is not derivable from anything else, it has its own emphatic existence which can be verified but not derived, which can not only be verified, actually you find no exception to it, at least in the domain of mechanics. Now, the mechanics that Newton addressed was obviously mechanics which addressed interactions between two particles, but the electrodynamic interaction and so on was not considered at Newton's time. So, once you start including electrodynamic interactions, then some of these things, some of these ideas have to be reinterpreted, and I will get to that as the course progresses at a later time. But we are going to leave out the electrodynamic interaction for the time being. So, in the context of the kind of mechanics that Newton dealt with, or everything outside electrodynamics and other interactions including the nuclear interactions, Newton's third law was always considered to be on the same footing in the traditional orthodox mechanics, but we will now actually derive it using a symmetry argument. So, let us see how this discussion will go. What we do is to begin with a symmetry principle, and the symmetry we invoke is translational invariance in homogeneous space. So, let me comment on each of the terms that we are referring to over here. Translational invariance, to translate is to have a lateral displacement, okay. you have got a certain object and you move it sideways or in this direction or in this direction. Okay. These are translational displacements as opposed to this, which is rotation. Okay. So, this is translation, this is rotation. So, these two are different operations, and you can change the configuration either by translation or by rotation or by a combination of both, because while executing the translation from this point to this point, you could also turn it, right. So, there could be a combination of both. What we are going to do is to consider translational displacement. We need the space to be homogeneous, and the meaning of the term invariance will automatically come when I comment on the homogeneity of space, because I am going to consider translational invariance in such a space whose properties are such that they do not change whether you consider the properties of that space in this part or in this part or in this part. So, I could consider a translational displacement from here to here to here, and the properties of the medium, the properties of space will not actually change. Consider this displacement, I consider this water bottle and move it from here to here, and I moved it in this space, and the medium over here is this mass of air which is around this, and it is also the same. It is not carbon dioxide here and oxygen here, okay, it is the same here. So, I could say that the properties of space have not changed, but perhaps if you look at very microscopic level, they may have changed, because who knows what exactly is the constitution of a mass of air over here compared to what it is over here. There could be some minute differences. The differences may be in the relative proportions of oxygen nitrogen, may be a minuscule difference, and if not, the kinetic energy of all the molecules, the individual kinetic energy of all the particles could actually be different. So, when we talk about this invariance, we are referring to such a system, such a space which has completely identical properties whether you consider this part or this part or this part, and these properties must be entirely homogeneous. There must be absolutely no change of any kind even at the microscopic level. Is that clear? So, that is the kind of invariance that we are talking about. This invariance is referring to the fact that the properties would not change when you go from here to here to here under any translational displacement. So, this is the kind of medium that we are talking about. There is a symmetry which is involved, which means that if you keep an object over here, it will find itself in an environment, but if you displace this through a translational vector, it would find itself in a new environment which will be completely identical to the previous environment. The identity of the environment after the displacement is the invariance. Is that clear? So, we are going to consider a symmetry principle which refers to translational invariance in homogeneous space, and in such a space which is homogeneous, and now we understand what a homogeneous space means. In such a space we consider an n particle system, a system of n number of particles, and we are going to consider a displacement of the entire n particle system through a small vectorial displacement which is delta s. So, there is a vector arrow on top of this displacement vector, and the entire n particle system is moved n block from one part to another, the difference vector being delta s. it essentially means that each of the n particles undergoes exactly the same displacement. And the n particle system is now going to find itself in a new environment. Obviously it has moved, but the new environment is completely identical to the previous one, because we are referring to homogeneous space in which translational invariance is preserved. Okay, so that is the kind of displacement we are talking about. Actually there are 4 essential considerations in this kind of a displacement. First of all, each particle of the system is considered to be under the influence of only the remaining n minus 1 particles. In other words, we are talking about an isolated system. There are no external forces. It is not that there is no force on any particle. There is a force on each particle, but whatever force is there on each particle is strictly what is generated by the remaining n minus 1 particles. Other than this, there is no other force. Okay? So, there is no other external force. Second, the entire n particle system is deemed to have undergone simultaneous and identical displacement. Okay? I want to rub this point in because it is an important consideration, which means that all the interparticle separations will be preserved, all the interparticle orientations will also be preserved, that whatever orientation a third particle has with reference to some other pair of particles, that relative orientation will not change when you consider this displacement. The medium is homogeneous and it spans the entire system both before and after the displacement. So, the properties of the entire medium, so it is not that some part of the system remains in the previous medium and then it goes to some other part where the properties have changed. So, the entire medium is considered to be homogeneous. And finally, the displacement of the entire system is considered to have taken place at a certain instant of time. Now, where does time come into the picture and why does it come into the picture? It is an important consideration because it will alert you to the fact that if you were to think of such a displacement, suppose I ask you to take a set of n particles and I give you a homogeneous space and ask you to displace the entire n particle system to a new configuration which is displaced from the previous configuration, how would you do it? Suppose you have got a few objects laid out on this table. I can move this laptop from here and keep it over here. I can move this wristwatch from here and keep it at the same relative distance from here, so that it will look identical at the end. But if I were to do that, it would take me some time. Yes.
I'm going to say there is no time delay between the displacement.
It is done at an instant of time, at a certain instant of time. Yes. So
but isn't that just a restatement of the second
condition? It is. It is rubbing it in. It is a simultaneous identical displacement. You are quite right. It is rubbing in the fact, but it states it differently. It underscores the fact that it is at a specific instant of time, which really means that if you were asked to displace an n particle system in this kind of manner, you would really not be able to do it. You would physically not be really able to do it. This can only be a mental thought process. Yes, you have a question.
Is it an ideal case or is it practical?
This is not practical. This is not practical. Good point. And that is exactly what I am trying to emphasize here. You cannot do it. Okay, physically, if you were asked to do it, you would not be able to do it. You can only think of this as a mental thought process, and the implications of this are the following: that the displacement considered is only a virtual displacement, it is only there as a phenomenon in your mind. It is a mental thought process, and such displacements are what are called as virtual displacements. Okay. This is the meaning of a virtual displacement. It is not a physical displacement, it cannot be really executed, it is not practical as you point out. I do not like to use the word ideal or non-ideal. I think referring to it as not practical is a practical way of saying it. Okay? This process is not practical, you cannot actually do it. So, it is only a mental thought process. Since real physical displacements would require a certain amount of time over which these displacements can be executed. So, it is not a real physical displacement, it is what is called as a virtual displacement, and in our mind nothing stops us from conceiving such a situation, because we are interested in the properties of the space and what is it that this leads us to, and that is the intellectual thought process which we have engaged ourselves with, and we will see that it has got amazing consequences. It is obviously redundant to ask what agency has caused it. You do not need a physical reason for it, it is not even a physical displacement. Okay. If I were to move this bottle here, I will need to answer how did the bottle get there, and then I will need to explain that okay, I pushed it. But since this is a virtual displacement, the question of what agency caused this displacement is irrelevant. So, we do not get into that argument at all. Now, internal forces cannot do any work in the virtual displacement, that should be self evident, right. Internal forces would do no work in this displacement, and the work done by the internal forces would therefore be 0. And this work done, and as I mentioned in the parenthesis over here, rather not done, because no work is really done. But if you were to determine this work done at all, it would turn out to be 0, and this work is what is called as a virtual work. Okay, now the terminology should be self explanatory, because it is the work done, or rather not done, by an agency which is not relevant to the process of the virtual displacement at all. Okay. So, we write the virtual work done to be 0, which is delta W, which is the component of the net force along the displacement. So, if Fk is the force on the kth particle and you sum over all the particles k going from 1 through n, then this total force, when you take the scalar product of this with the displacement vector delta s, then this scalar product must vanish, and you can write the force on the kth particle as force on the kth particle by the ith particle I summed over all the particles from 1 through n except I equal to k, of course. So, this is the force due to all the remaining n minus 1 particles. I emphasize this point that these particles are interacting with each other, but there is no external force acting on it. So, it is not that there is no force acting on each particle, but whatever force is there is what is imparted only by the remaining n minus 1 particles, no other forces involved. Okay. So, 0 is equal to delta W. So, this relation is now quite clear, hopefully. Okay, now this is an important result. Now, let us see the consequences. Now, this particular technique that we are using, this idea of virtual displacement and virtual work, this was introduced by D'Alembert, and I do not have any French student in the class, so I can get away pronouncing Alembert's name any which way I like, but I am sure that either T is silent or B is silent or M is silent or I do not know what. So, pardon me if the pronunciation is not correct. I can assure you it is not correct, and I have no idea what the correct pronunciation would be like. If it happens to be correct, it can be the biggest accidents I have ever had. So, these techniques were introduced by D'Alembert, and this is sometimes also referred to as the D'Alembertian principle, etc., etc. There are various names, or the principle of virtual displacement, or the principle of virtual work. Okay, all of these things go together, and D'Alembert is the person who proposed this mathematical technique. And now let us ask, under what condition can this relation hold regardless of the displacement vector delta s? Now, we never specified what this delta s must be. Delta s, we simply said, is a tiny virtual displacement. Did we say that this displacement should be toward east or toward west or toward north or south, any direction? It is completely arbitrary, and no matter what this delta s displacement is, in whatever direction it is, this relation must hold. It can of course hold if delta s and this summation of all these forces in this beautiful bracket over here in this first term over here, if this delta s and this net force were orthogonal to each other, the scalar product of course would vanish. But that would happen only for a particular direction delta s, which is orthogonal to this net sum of the forces. If you consider some other direction delta s, then of course you cannot invoke the 0 value of cosine theta to explain that expression, right. So, if this relation is to hold, no matter what the direction of delta s is, no matter what its magnitude is, and no matter what its direction is, regardless of the magnitude and direction of delta s, if this relation is to hold, then there is only one possibility, that the sum of the forces must go to 0. Okay? Now, that conclusion cannot escape us. So, the sum of these forces in this beautiful bracket, or what is expanded in this larger beautiful bracket, in which the force on each of the kth particle is written as the sum of the forces on the kth particle due to all the other particles I going from 1 through n, I not equal to k. So, it is this overall force which must vanish, and that guarantees that this relation will hold. Now, we have a very fascinating result. Look at this. You set this net force equal to 0, this conclusion cannot escape us, and we will accept Newton's second law, okay? And we know that having accepted Newton's second law, we would have implicitly accepted Newton's first law as well, because Newton's first law is in fact the first law and the second law is the second. There is a certain sequence in the thought process. You cannot get to the second law without identifying an inertial frame of reference, which is the first law, which is a statement of equilibrium, right. So, we would have used Newton's first law and second law, and using the first and the second law, we can write this each force on the kth particle as the rate of change of momentum of that kth particle, which is the statement of the second law, and sure enough we are using it. And if you simplify this relation, you can take the time derivative operator outside operating on this total sum, which is the total momentum of the system. Okay? So, the fact that the total momentum must be constant since its time derivative vanishes is a result which has now come from the homogeneity of space and from the consideration of translational invariance in homogeneity of space. And what does dP by dt equal to 0 boil down to? That if you take just a 2 particle system, that dP by dt equal to 0 means that the rate of change of momentum of particle 2 must be exactly equal and opposite to the rate of change of momentum of particle 1, and that is the same statement as Newton's third law, right. So, this is really amazing, because we have actually deduced the third law. We did not begin by a statement that okay, this is a fundamental principle. We accept Newton's first law as a fundamental principle, then we accept Newton's second law as a fundamental principle, then we go to symmetry, then we consider virtual displacements, we consider the virtual work done, and from the properties of invariance we actually deduce the third law, and what we have discovered for ourselves is a path that given symmetry considerations you can actually discover a law of nature. You can take it far enough, not just to Newton's laws. There are other laws in physics. Newton's laws do not provide a complete set of laws in physics, they do in the domain of classical mechanics, but in fact even in classical mechanics only to certain with certain restrictions, because if you get into electrodynamics then Newton's laws cannot be used just the way we normally refer to them, because when you get to electromagnetic fields you do have to take into account the momentum which is carried by an electromagnetic wave, and that is something which Newton never thought about. There was no need to do that at Newton's time. The laws of electrodynamics were not known. So, this came much later, and therefore, the Newtonian laws actually have to be reinterpreted even to accommodate the electrodynamic interaction. But we do have a technique that by exploiting the connection between symmetry and conservation laws we can actually discover new laws. Yes.
Can we deduce the first and second law with this same principle?
No, we cannot. Means at least there is nothing that I know of there is from which we can deduce the first law or the second law. First law is a fundamental law. I do not think that it can be deduced from anything. The second law is a statement of cause and effect relationship. It is a linear relationship between cause and effect, but one can do away with this relationship. So, one can do away with the second law in an alternate formulation of mechanics which I am about to introduce. So, you can do away with it and using the principle of variation which I will be introducing shortly, and then you will not really need F equal to ma to solve problems in mechanics. You will have an alternate way of solving problems in mechanics, but I will get to that. But the first law I doubt if one can do away with, and it will have to be accepted as a fundamental self evident principle which you are free to challenge and conduct experiments to verify it, and the fact that you find no exception to it is what elevates it to the status of a law of nature. So, that is what makes it a law of nature. I think at this point I would like to comment once again on the question which Siddharth had asked last time as to why is it, means what is the difference, what is it that you call as a law of nature? Do you call symmetry as a law of nature? And as I pointed out in the brief answer I gave last time, that the expression law of nature or law of physics is used when you talk about the description of a process which explains the evolution of the mechanical state of a system. Okay. Given a state of a system, and in classical mechanics the system is described by position and velocity, what is the law which will give you an explanation for how the state of the system changes with time. Now, when you do that, you are talking about what you call as a law of physics or a law of nature. Symmetry typically refers to changes that you can bring about through certain geometrical transformations, okay, like rotation about an axis or displacement. These are symmetry considerations, but these are geometrical symmetry considerations, which is the context in which one normally talks about symmetry. There are, however, other symmetries which are known as dynamical symmetries, and I will come to them a little later, but for the time being we will restrict ourselves to geometrical symmetries, okay. But symmetry is that property which leaves a system in under certain invariance after you carry out some geometrical transformations. So, that is where you use the term symmetry. So, you do not refer to it as a law of physics or law of nature, but you call it as a symmetry principle. So, what we figure out is that it is not really necessary to introduce the third law as a fundamental principle, because we have actually deduced it from a symmetry principle. It is derivable from something else, okay. And what we have done is to place symmetry ahead of the laws of nature, and this is an approach which I mentioned earlier, began with Einstein, and it is contained in a very deep theorem known after Emily Noether. This is known as the Noether's theorem. What it states is that for every symmetry principle there is a conservation law, and associated with every conservation law there is a symmetry. There is a one-to-one relationship between symmetry and conservation principle. Now, this is a rather popular statement of the Noether's theorem. In its rigorous form, one can state it using field theory, which I will not even attempt as part of this course, but in a nutshell this is what it really amounts to, that there is a close connection between symmetry and conservation principles. And what Wigner did was to elucidate these connections in a very beautiful, very lucid manner and very rigorous manner, because he considered all the symmetry operations. When you consider all the symmetry operations and put them in a set, you get what is called as a mathematical group, and using group theoretical arguments one can bring out the relationship between symmetry and conservation laws in a very nice manner. So, Wigner's name should also be mentioned over here, because he elucidated the connections between symmetry and conservation principles using group theoretical methods in a very lucid manner. So, this is the statement, or this relationship between symmetry and conservation laws is what is at the heart of Noether's theorem. Wigner explained this and elucidated this very nicely using group theoretical arguments, and symmetry is now regarded as the most fundamental entity whose form would actually govern physical laws, and you can therefore hope to deduce physical laws by examining these relationships. Now, we have seen this connection, but this connection becomes even more transparent if you formulate the laws of mechanics using a different approach, and the difference is with reference to the Newtonian scheme. Now, what is at the heart of Newtonian scheme is the recognition of equilibrium and its connection to an inertial frame of reference, right. The intimate relationship between equilibrium as a property of an object whose motion is self sustaining in an inertial frame of reference, which is the first law, and the cause effect relationship that when there is an interaction to which this object is subjected, if this object is imparted some kind of force, as would happen if it is involved in an interaction with any external agency, then its equilibrium will be disturbed, and the manifestation of this disturbance is acceleration. The velocity would change, and if it changes, it would change at a certain rate, which is dV by dt. This is what you call as acceleration. And this is the effect of the force which acted upon the object. So, this effect, which is acceleration, is directly proportional to the force, and the proportionality is the inertia. So, F equal to ma comes out of that. Okay. So, force is interpreted as the cause of acceleration. There is this is a linear response theory, as you can see. Acceleration is the response to the cause, which is the force, and this linear response theory invokes force, the idea of force, but there is an alternative scheme of mechanics which will make no use of force. I just mentioned a little while ago that you can develop a scheme of mechanics in which you really do not invoke F equal to ma at all. Leave alone F equal to ma, you do not even invoke the concept of force at all. This alternate scheme of mechanics makes no reference to force. It will not use Newton's second law, it does need the first law, however. Okay. So, this mechanics, it has a starting point which is similar to what Newtonian mechanics also has. The starting point in Newtonian mechanics was that a system is described by position and velocity, because we agreed that we must first identify the system, and the system, a mechanical system, is characterized by its position and velocity. And the question in mechanics is posed by asking, how does this evolve with time? So, how does the position change with time? How does the velocity change with time? This is the question in mechanics. When you answer it, what answers this question is the law of mechanics, or it is the law of nature. Okay? That is what you are trying to explore. So, this alternative scheme that we are about to introduce also begins with the same fundamental recognition of the fact that a mechanical system is described by position and velocity, equivalently by position and momentum. Okay, so, that alternative within the scheme exists, and if you describe it in terms of position and momentum, you will then ask, how does the position change with time, and how does the momentum change with time. So, you will look for equations for dq by dt if q is the position, and for dp by dt, p being the momentum. Okay. If you describe it in terms of position and velocity, you will look for dr by dt and dv by dt, which is acceleration. Okay. And that is what the equation of motion does, which is to give you rigorous mathematical relationships between position, velocity, and accelerations. So, we are going to have the same kind of beginning, which is to describe the mechanical system by position and velocity, but with a small difference. If you have a well defined function of position and velocity, you know what a function is. Okay? You have a function which is a dependent variable of an independent variable. Okay? So, given x, you know f of x. So, that is a function. This is a relationship that comes to our mind when we talk about a function. So, we will make use of a function of position and velocity, and if this function is a well defined function of position and velocity, then given the position and velocity, this function can also be known easily. And the statement of this alternative scheme is that a mechanical system is described by a function of position and velocity rather than by position and velocity itself, in a certain sense it is obviously determined by position and velocity. So, the starting point conceptually is the same, but you write it in terms of a function of position and velocity rather than q and q dot itself. Okay? Q being the symbol for position, q dot being the symbol for velocity. Q dot is just a dot placed on q, or which stands for dq by dt, which is the time derivative of q. You can also express the mechanical system by a function of position and momentum. So, it can either be a function of position and velocity, or else equivalently a function of position and momentum. So, the functions that we have in mind are the following: q is the position, q dot is the velocity, and a function of position and velocity that we have in mind is what is called as the Lagrangian. Okay? And this Lagrangian can obviously describe the mechanical state of a system. It is completely equivalent to saying that position and velocity characterize the system, but instead of doing so directly, it is characterizing the system in terms of the Lagrangian, and we will have to find out what kind of a function is it. So, we will discuss that now. And if you were to describe the system by q and p, by position and momentum, you can equivalently describe it in terms of a function of position and momentum rather than position and momentum itself, and this function of position and momentum is called as the Hamiltonian. Okay? There are some additional riders which I will not get into at this point, but this is the basic description of a Lagrangian and a Hamiltonian. Now, the principle that we are going to invoke is what is called as the principle of variation. What was the principle which was at the foundation of Newtonian mechanics? It was the principle of causality and determinism, that force is the cause of the effect, which is the acceleration, right. The cause determines the effect. This is the principle we were invoking. So, the principle of causality, the principle of determinism, or the linear response of a system to an agency, right. These are the principles which go into the Newtonian formulation of mechanics. In all of this, force has to play a role in Newtonian mechanics, because that is the very cause which is invoked in the principle that is used in Newtonian mechanics, which is the causality principle. The cause that you are talking about, the cause that the principle of causality refers to, is nothing but the force. So, the idea of force is intrinsic to Newtonian mechanics, but this alternative formulation of mechanics does not require it. It will invoke a different principle, not the principle of causality, not the principle of determinism. It will not invoke force. What it invokes is what is called as the principle of variation. This is also referred to as the principle of least action. More correctly, this is called as the principle of extremum action. It can be stated even more rigorously by referring not just to an extremum, but to what is called as a stationary point, and some of these things will become a little clear, but let us not go ahead of ourselves. This alternative formulation is based on a principle which is called as the principle of variation, popularly known as the principle of least action, although it needs some sharpening, okay, when you go to more subtle applications. So, some sharpening will have to be done, but popularly it is referred to as the principle of least action. And what might come to your mind when you talk about principle of least action is to become lazy, go to sleep. That's not what this is about, okay, although that is probably a larger and a stronger law of physics, I think, or a stronger law of nature, if not a law of physics. But anyhow, this is the principle of least action, and what the principle of least action or extremum action will do in its various incarnations, it will apply to everything that is happening around you. Using that, you will be able to answer the same questions you did when you use Newtonian mechanics. We agreed that using Newton's laws, you do not have to learn anything else. If you want to explain the trajectory of a ball which is hit in cricket, or you want to explain how rockets rise against gravity, or you want to explain why water flows in a particular way, or anything that any mechanical phenomenon, no matter what, okay, whatever you want to explain, you can explain it in terms of Newton's laws. Likewise, you can explain all of this using the principle of least action, and then you will not require F equal to ma to do this. The principle of least action will help you answer all of these questions. Every mechanical phenomenon that takes place in nature is explainable, you can explain it using the principle of least action, and this has got a very interesting history. Its precursor is the Fermat's principle, and what the Fermat's principle does is to explain why light takes the path it does when it meets the boundary of a medium. We do know that whenever a light ray hits the boundary of a medium, it gets reflected or refracted, and it does not happen till it meets that boundary. Till it meets the boundary, it keeps, we can talk about what we often refer to as the rectilinear propagation of light, that light rays travel in straight lines. But when it does meet a boundary of a medium, then some part of it gets reflected, some part of it gets transmitted, and why does this happen is explained by Fermat's principle. And what this principle states is that light travels from one point to another along such a path as would take the least time. Okay. Now, this again is a popular expression of the Fermat's principle, because this least time is a more common experience, but it can also be the most time in some cases. So, it can be an extremum, okay, but usually it refers to the minimum time, which is why it is called as the principle of least time. So, this is the Fermat's principle. Now, this Fermat was a very interesting person. He was actually a lawyer, and mathematics was his hobby. Now, how interesting. I think when we think of hobbies, we think of either reading, listening to songs, movies, watching games, and Fermat was a lawyer whose hobby was to study mathematics and of course physics as well. Fermat is perhaps best known for what is called as Fermat's last theorem, and this theorem is rather well known, and what Fermat wrote is to divide a cube into two other cubes, a fourth power, or in general any power whatever, into two powers of the same denomination above the second is impossible. So, here you have an example. You know that x square plus y square is equal to z square, which is really the Pythagoras theorem, right. So, if you look at the right hand side of this, it is z square in Pythagoras theorem, and what you have done is to break this into two similar pieces, x to the power 2 and y to the power 2. Now, can you write z to the 3 as a sum of x to the 3 plus y to the 3? The answer is no. Can you do it for x to the 4 plus y to the 4 equal to z to the 4? The answer is no. And you can't do it for any power higher than 2. That is Fermat's theorem, and he did not write the proof for it, and he said that he did not have enough space in the margin to write the proof, but he knew what the proof is. and this was in the 17th century, as you can see, and it took 350 years to prove this theorem. This was proved in not too long ago, less than 2 decades ago, in 1993 by Andrew Wiles, and it took like 350 years to prove this theorem, but now the proof is known. So this is Fermat's last theorem, and this is what Fermat is best known for, and here I alert you to the fact that the time taken by light is not necessarily a minimum, it can also be a maximum. So it should more correctly be stated as a principle of extremum rather than least time, it should be stated as extremum time rather than as least time, and even more correctly as follows, that the actual ray path between 2 points is the one for which the optical path length is stationary with respect to variations of the path. So this is a more accurate statement of the Fermat's principle, okay, which means that if you consider any path and you consider any small departures from that path, deviations from that path, then the actual ray is the one, the actual path would be the one for which these variations would vanish, okay. That is how it can be more correctly stated, but usually it is referred to in the context of the minimum, that light travels along a path that takes the least time. So I guess we want to take a 5 minutes break here, but I will be happy to take some questions.
Can you elaborate on this third statement, the actual ray path?
Yeah, I could, but this is a fairly involved issue. See, when you talk about an extremum, okay, or a minimum or a maximum, can I use the board? Like if you plot a function and this is your independent variable and this is your dependent variable, and this changes, and let us say it has got some functional dependence whatever, then this function does not change its derivative, which is delta f by delta x in the limit delta x going to 0. If you look at this at this point, okay, this derivative vanishes, and this is the maximum. Same thing happens over here as well, which is a minimum. So here you have a minimum and here you have a maximum, right. On this condition that the function does not change if you consider infinitesimal displacements about that point, that is what makes that point an equilibrium point, okay. It is a stationary point. If you keep a marble, a tiny marble which is like a point marble over here or over here, it could stay there forever, okay, because it describes equilibrium. There is no gradient there, there is no change in the force if this were a potential function, okay. But it could be either a maximum or a minimum, and in both cases it is generally regarded as an extremum. Now whether it is a maximum or a minimum can be determined only by looking at the second derivative, because here if you look at the second derivatives, then you will have slopes which go like this, right, and here they will go like this. So they will change in a different way. So unless you look at the second derivatives, you cannot really classify whether it is a maximum or a minimum. As a matter of fact, there are more complex stationary points, saddle points for example, but I will describe them later on. So these are matters of details, and typically our discussion in the context of our discussion, we will be referring to this as an extremum principle, more commonly as the principle of least action, and that is what I will introduce in the next class.